each TAs has different level of leniency. You may be luckier in one case and luckier in another case, so please tolerate that. So we have a grading scheme, and I have asked all the TAs to follow that grading scheme as closely as possible, but minor variations will be there. Okay. And if you say something like this, I will really check. So if you say, hey, my friend is doing, you submitting the same code and he get higher marks, then I will really check whether your code is the same or not. If you got, you really have the same code, I will actually penalize you. So if just a minor variation, fine, let it go. But if there is a huge variation, one got 100, the other got 50, for example, for or whatever reason, then tell me. Minor variation, ignore. Second, I have made 2 announcements in the game system. So if you have, please check the main page of the game system quite often, because I'm not going to use IVLE announcement for this, for game-related things. So for example, last week, some of you asked, can I edit the run method? After I look at the requirement, yes, you have to. Okay, you may want to do this. So I changed I relaxed the constraint. You can edit this if you need to do so. If you don't understand what's the purpose of this, then you have to ask your friend why this matters, because that means you haven't understand one thing. Right? Okay. Next is late submission policy. Okay. I have detected almost about 5 late submissions for PS2, and that is a bit too many according to my opinion. So if you're late, immediately submit email your TAs, your lab TAs, not your tutorial TAs, your lab TAs, because the submission system will forbid you to do so after deadline. Right, and this is the new policy to minimize such late submissions. Late by 24, 48, 72 hours, you'll get 5, 10, 20 penalty points. And after that, it will be literally 0. So if you submit on Sunday morning, it will be -5. Monday morning, it will be -10. Today, just now, 2 hours ago, is -20. Beyond that, it will be ignored. So to avoid missing that line, there are several tips. So if you have coded, for example, subtask 2 solution, and then you still want to improve that, and this is still before that line, then why don't you just upload your current code and keep improving your solution? If you manage to do so, re-upload the better one. At least you will have non-zero submissions already, right? So do that rather than keep improving, and then forgot that you have gone past the deadline. Right? And for every PS, I have written the deadline carefully in the first page. So this one. Okay. So see that for PS3, the deadline is not this Saturday, but Tuesday, 24 September, during your recess week. Because I know that most of you will do quiz 1 with me this Saturday. Okay. So look at the deadline carefully. And if you visit our IVLE page, you should be able to check all the details, week by week details of what we are going to cover that week, when the PS is going to due, and so on. And that is. Okay, so use this information to plan your timetable. Right. And finally, quiz 1 is this Saturday. I don't have any more plan to run official help session, but if you have questions, post in IVL forum, or if you really have private questions, you can come to me during office hours to find me. Okay? Alright, so let's continue with, this is where we left off last week. I stopped at breadth first search. So hopefully I can run today's class in 3 segments. First segment about 30 minutes, I will clear this, lecture 5, and then take a 5 minutes break, and then run the first algorithm for minimum spanning tree, Prim's algorithm, and then we take another 5 minutes break, and then the third segment, the crash course algorithm. Yeah, let's see whether we can do that. Okay, so last week I have shown you breadth first search. It's a way for us to search or to traverse a graph, to travel along our graph. You need a source vertex, and you will breadth first search will visit the neighboring vertices layer by layer. It will first visit those that are direct neighbors of your source, and then it will visit those that are 2 steps away from the source, 3 steps away, 4 steps away, and so on. To do so, it requires several helper data structures. You will need a queue to order this. You order this visitation. You will need a Boolean array to flag whether I have visited or have not visited a certain vertex. And then lastly, optional, I need a predecessor array to reconstruct the path again in the future. Right, so we are going to see depth first search, which have the similar structure, but the way depth first search organize the neighbors is different. We are going to use a stack to do so. Okay. So depth first search also have the same idea as breadth first. You start from the source. If you can reach your neighbors, go. If then you can still reach another unvisited neighbors, go to that unvisited neighbors, and so on. Keep doing that until you cannot visit any more neighbors. You backtrack and continue. The analogy is a maze like this. So suppose you start from this point. Yeah, you start from this point. Suppose I take a right turn all the way to here. When I hit this, I cannot proceed any further, right? So I'm here. Can you see? I'm here. Look at my pointer. Now I have to backtrack. At this junction, I have options. I can go up, and then I can go right. I can go left. I can go left. Go up and then left. But at this point, again, I have no more choice. So what should I do? I backtrack. So where's my pointer? Okay, I backtrack here, backtrack. At this point, I have choice. I have choice again to move up. So that's roughly how depth first search works. Imagine that you are a human, you are yourself. You want to escape from a maze like this. Since you cannot split yourself into 2, you have no choice but to try one path. If it's a dead end, no choice, right? You have to go back. And how to go back? You will need a help. Like you can lay down a marker to tell yourself that you have just been there before. So when you backtrack, you know where to go. If you don't have it, you will be lost inside, something like that. And we are going to use stack for that. Yeah. So depth first, we visit the vertices in G in depth first manner when viewed from source S. So how to maintain this? We are going to use a stack, but we are not going to use explicit stack, but we are going to use built-in stack inside recursion. And this tree is the same. How to differentiate whether a certain vertex has been visited or not, so that we don't repeat. We use a Boolean array or Boolean factor. Yeah. And lastly, how to memorize the path? We use a predecessor array or parent array. I call it P. Later, at the back of this lecture block, I will show you how to use P. And during tutorial, we will also use P, predecessor information. Right. So the pseudocode that you will later convert into code if you do PS3 or PS4 or something like this. You first set all the values in visited, all the cells in visited to be 0 or false, and then predecessor information for every vertex to be -1, right? And then we recursively call. So I put the name DFS recursion bracket S starting from source. So what does this recursive function do? This recursive function has one parameter where we are now, which vertex we are now at. We will set that vertex to be visited so that later when we revisit this one again, we will not do so. We will not go to the same vertex again. Then we have this loop for all V adjacent to U, the neighbor of vertex U. If my neighbor is not visited. If not visited, then I will say my neighbor, you are now, the predecessor of my neighbor is me, and I will recursively go to my neighbor. Okay, this simple code will behave that first. Let's see how it works on this simple graph. Right. This is a static PowerPoint. I have the animation already, visualization website that run this that first. So at the beginning, let's just use the scripted version first. Let's look at this graph. This graph has 3 components: 0, 1, 2, 3, 4, and then one component, and then 5 isolated vertex, another component, and then 6, 7, 8, and the third component. So if I now run depth first from this vertex 0, I will behave. The depth first will behave like this. First, it will flag 0 to be visited. Let's call it as black here. So later, when I see another black vertex, I will not touch it anymore. At 0, I have options. I can go to 1, right? I can go to 1. At 1, I have 3 options actually. I can go back to 0, continue to 2, or continue to 3, right? At this point, ordering of neighbors matters. You can then, when you are at vertex 1, you can choose to go back to 0, 2, or 3 in that order, or you can go to 3, 2, 0 in another order. Okay. All of these are valid, but to simplify our coding, we will assume that we will order the neighbors based on increasing vertex numbers. This is to simplify our implementation. Right? So, and when I'm in vertex 1, I actually look at vertex 0 as my first neighbor. But then I look at it, this one is already black, already visited equals to true. So I will not go to 0, because if I do that, I will cycle 0, 1, 0, 1, 0, 1 infinitely. Right? Now I'll consider my next neighbor of vertex 1. I'm now at vertex 2. Vertex 2 is still visited, vertex 2 is still blank, still 0. So I recursively go there. When I'm in vertex 2, again I have 2 choices. I can go back to vertex 1 or go to vertex 3. If I go back to vertex 1, the red edge here, I will visit a black vertex, the one that's already visited. So I will not do that. I will look at the next neighbor, which is vertex 3, and I continue there. At vertex 3, I have 3 options, 1, 2, 4 in that order. Vertex 1 and 2 have been visited, so I have no choice but to go to vertex 4. Right? 1 and 2 are both black already, so I can only go to vertex 4. When I'm in vertex 4, I have one option, go back to vertex 3, but this is already blocked, already visited. So actually I don't have any more options here. When I don't have any more options, I have to backtrack to previous state. And this is my previous state, right? But now I have visited 4. At vertex 3, again I don't have choice, because 1, 2, 4 now have been visited. So I backtrack again, and then done. When I backtrack again, I'm done. Yeah. The blue here, the blue edges, are called the depth versus spanning tree of the component or subgraph of the original graph when the depth versus is started from vertex 0. So if you draw the tree, it will be like this. Okay. 0 is connected to 1. 1, the predecessor of 1 is 0, the predecessor of 2 is 1, the predecessor of 3 is 2, the predecessor of 4 is 3. Then you can use the information to reconstruct back this tree, spanning tree. Okay. See that I don't have 1 tree, right? I have 1 tree. Alright. So let's analyze what's the time complexity of this depth versus. It's again V plus E. Why? Because each vertex is only going to be visited once. How can we be so sure about this? Because we have this visited flag, right? We have a Boolean array visited. Initially all 0 or false. Every time we hit that vertex, we will set it to be true, and we will never set this to be false again. And then inside our loop here, we only look for those that are still 0. So can you see by this reasoning that every vertex will only be changed from state 0 or not visited to 1 or visited only one time. throughout the execution of this algorithm. So if I have phi vertices, at most I can do this phi times. Right? So this is the first one. Y is at least OV. Now let's see what we do every time a vertex is visited. When a vertex is visited, for example, I visit vertex U. Right? I will flag this to be visited, and then I will explore my neighbors of vertex U. Sometimes I have 0 neighbors, sometimes I have 1 neighbor, sometimes I have 2 neighbors, sometimes I have phi minus 1 other neighbors. Right? But if I sum this all, I cannot exceed E edges, because there's a maximum number of, if you sum every neighbor, the total of neighbors of every vertex equals to E. Right? Vertex 0 has certain number of neighbors, vertex 1 has certain number of neighbors, vertex 2 has certain number of neighbors. So if you do this for every vertex, you have actually visited all edges. Right? So it's E or E. Assuming that we use a adjacency list. Right? We sum these two together, phi plus E becomes O phi plus E. Okay, what happens if we use adjacency matrix? If we use adjacency matrix, this process, this line, for all V adjacent to U, is no longer OK, where K is the number of neighbors that we actually have, but will be OV. I'm going to scan the entire row and enumerate my neighbors. For every vertex, you scan the entire row. So for every vertex, you do phi steps. Phi times phi squared. So if you use adjacency matrix, the time complexity of depth first search and also breadth first search will be slower. It will be phi squared. Okay, whether this matters or not, discuss this in your PS3, for your PS3. Right. Now we have seen how depth first and breadth first works. Once you have run depth first and breadth first, it will generate the values for P, the predecessor information. Now how can we use it for reconstructing the actual path? Right. So I can start from this ending vertex, which is suppose is vertex T. While this vertex is not the source, I will print it, and then I will say I is equal to Pi. So it means that I go back one step. So try this on this array P. Suppose after running the first search from vertex 0 just now for this example, right? Look at this yellow edges. These are the spanning tree, right? The first spanning tree. If I run the first search from this vertex 0, I have this value. Right? So suppose T is 4, where T is 4. This is the ending vertex. So I want to know what is the path from 4 back to vertex 0. So I will look at it. Look at this. At index 4, I know that my predecessor is 3. So I go back to vertex 3. At vertex 3, I know my predecessor is vertex 2. At vertex 2, I know my predecessor is vertex 1. At vertex 1, I know that my predecessor is vertex 0. And at vertex 0, I know that I am the source. So the path is actually 4, 3, 2, 1, 0, right? 4, 3, 2, 1, 0. 4, 3, 2, 1, 0. But do you see that it's reversed? It's from back to front, right? So if we want this to be front to back, there is another way. We can one way is to use recursion. We use recursion. So we rewrite the code slightly different with recursion. I call backtrack U. If U is not -1, or if U is not source, right? So actually you can change this to if I not equal to -1. You can also do that because the source doesn't have predecessor. So you can also use that information. You can change this one from I not equal to S to while I not equal to -1. Same, right? So this is another example. When U is not -1, U is equal to -1 means that I am at the source. I stop. But other than that, I will recursively go back first, calling predecessor of U before I output U. Doing so will reverse the output. If this is confusing, you have to improve your understanding of recursion. It will behave that way. You will go back first. When the recursion unwinds, then it will start outputting. That's why you will see the okay, let's see the example. At vertex 4, I recursively go to 3, 3 go to 2, 2 to go 1, 1 go to 0. 0 is minus 1, so I stop. When I stop, I will echo vertex 0, 1, 2, 3, 4 when I unwind the recursion. That's why the output becomes source to destination again. Right. And we already have this, so I hope that you use this for to help you understand the material. Okay. Let's use. Okay, this is the animation for breadth-first search that I have shown earlier last week. Okay. Okay, I make it very fast, but if you need to understand step by step, you can always do this. So you can pause it and then call next step, okay, to see what are the steps. You click next one by one to see how it behaves over time. In the future, I will improve this visualization to be able to do this, but not now. If you look at some other newer visualizations, we already have capability to do this, which is quite cool. I can rewind back to the starting point. So at the moment, if you look at your the deficit visualization, it can only go forward. I can stop it and then click next. But what did I saw just now? Can I rewind one step? I cannot. In the future, I will add this feature. Can go back to the starting point and go back to go anywhere in the process of the algorithm. So you can take a look. And not just that, in the future we will have will be linked towards the source code, so you will know where you are in the code also by highlighting the codes, something like that. Okay. This is still ongoing development, so we don't have it yet in the older version of breadth-first and depth-first. Okay. All right. So now you already know how breadth-first and depth-first roughly work. What can we do with them? What can we do with them? We can do several other things. Right? On top of adjacency metric and list, we can now do some other things. Okay? Knowing that breadth-first or depth-first, if you give them a starting point, a starting vertex, it will try to explore its neighbors, and so on until it really cannot find any more neighbors. So doing so, this behavior can be used to test whether two vertices, let's say vertex S and vertex U and vertex V, whether they are connected or not connected. So you start breadth-first or depth-first, either one, because they are essentially the same, but just different in the way of exploring. I start from source equals to U. I keep running, and when breadth-first or depth-first stops, I check this flag. Visited V, is it 1? If this is 1, I know that U, vertex U, can go to vertex V. Otherwise, it cannot. So, for example, I run breadth-first on starting from vertex 0. Then 0, 1, 2, 3, 4 will be flagged as visited equals to true. So if I ask, is 0, does vertex 0 can reach vertex 3? The answer will be yes, because visited 3 will be true by that point. But if I ask, can vertex 0 reach vertex 6? No, because vertex visited bracket 6 will be still false at the moment, at that point. Okay. Next, identifying components. So we can visually inspect that there are 3 components in this graph. 0, 1, 2, 3, 4 will be one component. You can visit each other from there, from this, in this side, this component. 5 is another component. 5 cannot visit anyone else. So it's an isolated vertex, but a single component. 7, 6, 8 is the third component. So visually we can see that quickly. For a small graph like this. If the graph is larger, even us human cannot do it easily because it's too complicated for us. So if computer wants to count how many components are there in this graph, we can modify or we can combine depth first or breadth first together to do this. Okay. Initially, I will have a variable CC. CC is connector component. I will say that there are 0 connector component at the moment, and then I will flag all visitors to be false at the beginning. Okay. For knowing that if I run a breadth first or depth first from certain vertex, I will be able to visit every other vertices connected to this vertex. Knowing this property, I will use it to count how many components that I have. Right? Look at this pseudocode. For all v in set of v, if I see that visitor v is still 0, I will increase the number of connector components by 1, and I will use depth first rec or breadth first search, BFS or DFS, from this vertex, and I know that these two algorithms will flag those that are reachable from vertex 0. So I'm going to do that in this example. So initially everything is not visited. So when I go at vertex 0, visitor 0, is it false? Yes. So I will increase CC to be 1. And then I will call depth versus rec from vertex 0. And I'll be able to flag 0, 1, 2, 3, 4 to be visited equals to true. But then depth versus or breadth versus will stop there. It will not be able to touch 5, 7, 6, or 8 because they are indifferent components. There are no way any vertices in 0, 1, 2, 3, 4 can reach 5 or can reach 6, 7, or 8. So breadth versus or depth versus can just simply stop there. Then my loops goes back here, right? For all v in the set v. Yeah. Now I check visitor 1 is it false? No. Visitor 2, no. 3, 4, 5. When I visited 5, I know it's false. So I will repeat this process. CC equals to CC plus 1. So now it's 2. And I will flag depth first search from 5. But then I will stop there. Okay. Then I will continue again. Visitor 6, is it false? Yeah, it's false. So I will make this 3. 6, go to 7, and then backtrack, back to 6, and then 6, go to 8, backtrack, and then done. And then when I check visitor 7, oh, it's already true. Visitor 8, oh, it's already true. Then I'm done with all vertices. How many values? What's the value of CC at the end? It's 3. So I can count how many components are there by calling depth first or breadth first from a representative of each component. Because I know that if I run breadth first or depth first from a certain vertex, everything inside that component will be visible. Right? So now a question for you. Such algorithm, what's the time complexity? Is the clicker working? No? Okay, I hide this first. Hide this first. Can some of you try? It's working. It's working. It's working. Okay. So, what's the time complexity of counting connector component? are 50 people with clickers, and I only saw 30 here, 29. Oh, where are they? Where are the rest? Oh. I think 30. Let's say 30. Divided. Okay, 11 says phi square plus Ve. Is it because I put the same number in PS3? 13 says V plus E. 6 says some other thing, some other. The answer is second one. Okay, why? Why is second one? Alright, OV. Yes, this is OV, right? But here, the fact that I will only run the first search if visited phi equals to 0 means that suppose vertex 0 is not visited. When I call DFS rect of vertex 0, I will visit all other vertices connected to vertex 0. And I will not touch everything else that I cannot touch. So, at the moment, it is not E. I am not exploring all edges, all E edges. I will explore some parts of the edges. When I visit 5, I will visit 5, but no edges. When I visit 6, I will visit 6 and these 2 edges. See that eventually at the very end, the amount of work that I did is I visit all vertices once, and I will only also visit all edges once, right? Yeah. So it's not phi times phi plus E, no, but eventually it's just phi plus E, because the way it works, it will visit each vertex once. Visited V will be turned on, will be set to be true, either by will be visited by this references or references. Every time you can visit all that members of the component, it will be set to true. So each vertex will be only touch one. And if reference or reference explores a certain component, it will only use edges in that component. It will not touch edges in other components. So eventually, when the whole thing stops, you have only touched all edges, each edge one. The overall complexity is E, phi plus E. Right? So this is a challenging slide. Next, what else can we do with that breadth first and depth first? This one will only work for depth first. So this one for this slide, breadth first, this does not work. Okay, so this one we are going to revisit again later in the third part of 2010 when we for topological sort. Right? So topological sort of a directed acyclic graph is a linear ordering of vertices in the directed acyclic graph, so that if I have a vertex and then I have an outgoing edges, vertex U is connected to vertex V, for example. U will appear on the left side, V will appear on the right side of the linear ordering. Let's use some examples here to clarify that understanding. Right? First, directed acyclic graph. A graph that has direction, say 0, 1, have an arrow, right? 0 go to 1 doesn't mean that 1 can go back to 0 because there is no back arrow. Acyclic means that this graph, there is no cycle. Once you go out from a certain vertex, go to another vertex, no way you can come back. Can you verify this? Let's try. 0 go to 1, right? Is there any way 1 can go back to 0? Either directly, cannot, right? Go away and then go back? No, cannot. From 0, once you go out, you cannot go back. How about 3? 3, you go out, you can only go to 4. But is there a way from 4, blah, 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 go back to 3? No. No, right? So if your graph has this property, we call this graph directed acyclic graph, or DAG or DAG. And this is a powerful concept for dynamic programming later. So, having a DAG, we can rearrange the vertices. Where's it? Do I have the example? Okay. Look at this. Same picture, right? We go to the slide first for explanation. If I have 7, 6, 0, 1, 2, 5, 3, 4, this is the linear ordering of the vertices in this graph. I have 8 vertices and I just number them left to right in one linear list. If I read these numbers one by one from left to right, I will never encounter any edge violation. So 7, 6. Up 7 can go to 6. See that 6 will be on the right side of 7. So it's valid. And then 0. 0, 1, 2, 3. See that 0 is connected to 1 and 2. See that 1 and 2 is on the right side of 1. And 1. 1 is connected to 2 and 3. See that 2 and 3 are on the right side of 1. 2 is connected to 3 and 5. So when I put 2 here, see that 5 and 3 are on the right side of 2. So if I read this number 7, 6, 0, 1 from one by one from left to right, I will never encounter a situation where I have a number, there is another number on the right, and then that number on the right has edge to me. You know, the edges can only go to the right side. If I read the numbers left to right, the vertex number from left to right. So 7 can only have edges to any to some vertices on the right side. Happens that 7 can go to 6. 6 happens that it doesn't have anything, so no violation. 0 can only have edges to some vertices on the right. Happens that it go to 0, 1 and 0, 2, right, which is still correct. This is an example of topological ordering. So how to generate that topological ordering? Okay, every deck has at least one or more topological sort. Okay. So how to find directed acyclic graph? There are several algorithms to do this, and what I'm going to show you is the simplest ever, the simplest that I know. 10 years ago when I learned this, I was presented with something that is too complicated. And as time goes by, I realized that finding topological sort can be done in a much easier manner. And the person called Robert Andre Targent formed this algorithm. He simply modified the emphasis to do so. So how do we do that? He said that if the graph is a deck, it's a cyclic graph, then simply running emphasis on it, and at the same time record the vertices in post-order manner. Post-order means after you have visited all your children, visit yourself. Same as post-order traversal in binary tree. Once you have go left, right, you visit yourself. Here, since you can have more than one children, after you visit all your children, visit yourself. If you do that, then you will get at least one valid topological order. So what Robert and Targent did is to add one line at the back of the emphasis recursion, appending the current vertex to the back of a certain list. I call it toposort list. This is called post order, right? Because once you have done visiting all your children, then you visit yourself. What else? And then in the main method, you same clear all visited, set predecessor to be false, clear the toposort list, and then for every vertex in V, if it's not visited, call this. At the end, reverse toposort and output. The answer will be reversed. Okay. So let's see the example here. So the way it works is roughly like this. I will call the emphasis from vertex 0, right? Then I will recursively call 1 go to 2, 2 go to 3, go to 4, backtrack, go to 2, go to 5, backtrack, go to 2, backtrack. Yeah, that's the rough behavior of the emphasis starting from 0 in this stack. Now, if I have visited all the vertices 1 and 2 and so on all the children, and then I finally visit 0, is it true that the toposort list will be something like this? List of vertices reachable from 0, at the end, vertex 0. So I start the emphasis from 0. After I visit all my neighbors, then the toposort list will be something, every vertices reachable from 0 in certain order. Let's just ignore the order. And at the back of it is vertex 0. At this point, understand? No? No? I repeat again. the way this code works is to append current vertex to the back of a certain list. That's how it works. So I run depth versus from vertex 0 on this graph. If we visit 0 equals like 1, 1 visit 2, 2, 3, 3, 4, backtrack, go backtrack, 2, 5, backtrack, 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 0, 2, cannot backtrack. That's how the depth versus works. Now, view from vertex 0, I have tried visiting 1 and all its connected members of this component, and then I backtrack. I try to visit U and all its connected component, and then backtrack. At this point, the list will be everything that is reachable from 0, and the back of it is myself, vertex 0. So far, okay? Okay. Now, let's think about this recursively. Now in vertex 1. Now in vertex 1. 1 can go to 2, 3, 4, backtrack, 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 4, 5, backtrack, 1. Try to go to 3, backtrack, done. When vertex 1 have visited all its neighbors and all other reachable vertices from the neighbor, and then I'm done, almost done, then the list will be everything reachable from vertex 1, and then at the back of it is vertex 1. And in the big picture, at the back of that is vertex 0. So if you keep doing this, you will eventually have this kind of list. And this kind of list, if you reverse it, you will get the topological order. Okay, don't worry, this will be repeated in tutorial class again. This is the, see, slow down here, last year's survey result. Yeah, I know that this is one of the more confusing part of depth research. We still have more time because we are going to use topological sort again only in week 9, I guess, when we repeat, when we discuss dynamic programming. We have time until from now until then to understand what this thing is doing. But the idea is just modify depth first search by adding vertex U to the back of a list. Right. So I closed lecture 5 by comparing depth first and breadth first. So there are pros and cons. For depth first, it can be easier to code for some of us. It uses less memory because you don't you only maintain where you are at the moment. You don't maintain a big queue. Has some extra features that can be useful for your PhD. I can only stop there. Right. We can discuss what does it mean in the discussion forum. The bad side is depth first search. One of the bad side is it cannot solve shortest path on unweighted graph. What does this mean? We will discuss this in week 7 and 8. For breadth first, it has a special feature. It can be used to solve shortest path on a special graph. Cons, slightly longer a bit, yeah, for some of us. Use more memory, especially if you use a large queue. Some graphs behave like that. For most cases, it won't matter much. Right? So we have done this. We have seen some terminologies. We have stored our graph, not just the edge, not just the vertex, but also the edges information. And then I've shown you depth first, breadth first, and depth first, and show how to apply it to some problems. We'll take a 5-minute break until 10:50, and I will start the first part of MST. If you have questions, you can come forward and ask me. lab here will show you again. It will show you how to store asymmetric list, convert between one representation to another. This Thursday, the topic is about graph data structures and traversal. So, see that. Graph data structure manipulation. And algorithms and implementation to solve up to subclass 2. We'll finish class, so you can ask your TA again on what's the exact details. Nice. Okay, we will start again. For those who are late just now, I showed this announcement at the beginning of the class. It's a minor one. One of the more important is quiz 1 is this Saturday. Don't forget about that. You miss it, you will lose 15%. And then second thing is in the work bin, I have actually uploaded more than one file. I don't just upload my lecture notes, but also some other files, right? You can use it for your advantage, you know. This is actually coding, the actual Java file, compilable and run. You can run this and see how deficits or brevices works. So you just compile and run this. You can play around with this code. So it's there not for you to be amazed of it, but to use it. So this is how to use it. Okay? Right? Use it, and you may want to understand this part first before you go to your lab for PS3. Actually, PS3 is just modification of this file. If you know what to do. If you know what to do, you just need to modify something from here. Which part, you need to understand what this code is doing first. Right. Now I go to lecture 6. Okay, lecture 6. I will go through 2 parts. Hopefully we can have a break in between. This is a short lecture. Why it can be so short? Because I'm using a trick. I'm going to make your TA work for this. So on week 7, they will share with you some parts of this lecture material. Alright. So what we're going to do, I'm going to briefly motivate you what is minimum spanning tree problem. You have seen this in 1231 for some of you, majority of you, whether you remember it or not. cs2010, discrete mathematics. And I will re-highlight 2 algorithms, 2 very classic algorithms, greedy algorithms, that can solve MST, standard MST. One is called Prims, the other is called Kraskell. These are 2 names, 2 algorithm inventor names. Both are greedy, both uses data structures that some of them we have used it before, some we haven't. So for Prims, we are going to revisit priority queue. We are going to revisit lecture 4 materials. For Kraskell, we are going to revisit sorting and something new, data structure to prevent cycle. This part, I will leave it to your lab TA on week 7. That's why I can go faster today. Right. Some admins for this, yeah. So PS bonus, which the name will be announced very soon, will be open after quiz 1. So after quiz 1, for some of you, this is a typo, so please fix this. After quiz 1, if you think you want to study more during midterm break, you can do this. But this is look at this. Okay? Non-CS2010R students do not have to do this. This is optional, and it is hard theory. Right? So if you want to have fun in your research week or study other modules, you can do that. There is you can get to level 15 without touching this PS at all. And if you touch this PS, you will confirm to get level 15 most likely. If you can do this PSR, PS bonus, you can do it perfectly. It's kind of guaranteed that you will end up in level 15 because the level of knowledge to solve this is high. And for those who are trying to do this, I have to say sorry in advance that your research week is ruined. Even some of my best IGM ICPC students needs more than 5 hours to do it. They can't do it, and most of them cannot do it on contest time in 5 hours. So they will need more time to fix what's the bug. So I think you will need much more time to do that. To complete the full version of, because there are subtask level, right? The last one is crazy. Okay. So if some of you for taking R version, if you think that PS2R is too easy, I did it that way. PS3R is too classic. Yes, it's designed that way. Your challenge is this one. Okay. So that's for 2010R students. And for the rest, the normal PS will only be open on Thursday. It's about MST, about what we discussed now today. Yeah, we only due again quite long. We only due on 9 October because I want to let you do other modules, concentrate on other modules on week 7. So as my promise, I will take your brain energy this week, concentrate on my quiz 1. And then after that, on research week and quiz week 7, I allow you to think of other modules. If you don't want to do PS bonus, right? If you still don't want to do PS bonus, then you will keep thinking about this module or every week, right? So that's the plan, right? That's the plan. Okay, so continue. Okay. So MST. So what you learned today will be applied in PS4, and you will need to use knowledge about minimum spanning tree to solve PS4. So, quick review. What have we learned before? We have seen three data structures. So what is a tree? Tree is a connected graph, 3 vertices, 3 minus 1 edges. And tree also have one unique path between any two pair of vertices in T. There's only one unique path. You can try drawing a tree, and there is only one unique path between them. So let's see this one. Okay, this is a tree, right? This is a tree. Let's take vertex 8 and vertex 6. There is only one way to go from 8 to 6, no other way. Okay? 8 can only go to 7, 0, 1, 6, and that's the only way to reach vertex 8. I'm referring to simple path. I'm not talking about 8, 7, 8, 7, 8, 7, 9, 7, blah, 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 and then 6. I'm not talking about that. The one that only touch every vertex once. There's only one simple, unique path between two vertices in the tree. And then we have another notion of spanning tree. I call it ST, spanning tree of the graph. Spanning tree is a tree that spans or covers every vertices in the graph. If the graph is connected, then breadths and depths will generate this spanning tree. If the graph is disconnected, then this spanning tree is only valid for that component. So let me highlight. Okay. Suppose I'm going to cut this vertex 7. Right? So I have one tree. Wait a minute. Suppose I have this kind of graph, right? I have this kind of graph. If I run depth first search on vertex 0, then I will have a tree. Okay, 0, 1, 2, 3, 4, 5, 6. Look at 6, 0 is dotted. It's not part of the 3 edges. 1, 6 also dotted. This is not part of the 3 edges. So if you remove these two, if you remove, so if you remove 1, 6 and 0, 6, they are dotted, right? You have a tree. But this tree is only spans this component, because I have 8 and 9, they are not connected to it. So spanning tree is like this. Okay, a tree that spans or covers every vertices in G, and for breadth-versus and depth-versus case, if the initial graph is not connected, then the resulting tree is only valid for that component. Right. And we also have seen sorting in 1020 in several sorting algorithms. This is just a way for us to rearrange a set of items, set of objects, so that for every pair of them, I have A less than B. So I can compare the objects, and I can rearrange them in sorted fashion in this sorting problem. Okay. So just to have a quick check on your understanding of tree. Is this a tree? And I draw it this way to break certain misconception about tree. Yes or no? I saw 30 clickers so far. Just now. Okay, 31. Good. Let's see. Good. Yeah, this is a tree. So a common misconception is a tree always written as a root, and then it has children, have grandchildren, something like that. Not always. A general form of a tree can be written, it can be drawn this way. As long as it's a connected graph, it has phi edges, phi minus 1 edges, phi vertices, then it is a tree. There's only one unique path within every pair of vertices is a tree. Now, if the edges highlighted in red part of a spanning tree of the original graph, so I have an original graph with 3, 5, 4, 5, 5, 0, and so on. I have these red edges. So are these red edges spanning tree? Yes or no? If yes, why? If no, why? Okay. Just see 28. It's no. Yeah, the answer is no. Why? Right. First, the red edges is not a tree in the first place. It's not a tree in the first place. Why you have a 1, 3, 3, 2 is a cycle actually, right? So 3 cannot have cycle. 3 cannot have cycle. And then, so although I have 1, 2, 3, 4, 5, 6 vertices, and I have 1, 2, 3, 4, 5 edges, this is not a tree because this is not connected. Vertex 0 is isolated. So suppose I take out 2, 3 edges, the red edge 2, 3, and store it in 5, 0, then it is a spanning tree. Next. So with this, I want to extend our knowledge a bit and link this back to MST. And I'm going to give you an example on why MST can be a good solution for certain real life problems. Right. Suppose you are a member of a government and you have a villages like this. So suppose these are some village, some smaller village, some bigger village, and so on. Okay? Separated with forest and open space and some other forest and so on, something like this. Suppose we have 5 villages like this, and then you want to build, you want to link these villages with roads, and the cost to build a road depends on the terrain. So, for example, I want to build a road that cuts through a forest. What should I do? I have to cut down the trees, right? I'm cutting down the trees first. If I want to build a road over a mountain, what should I do? You either build roads that go up and then go down again, or you build a tunnel, right? So, given the terrain, the cost of building a road between two places can be different. So, you only have limited amount of money. How are you going to build the roads? Okay, so you just want to link them. So, can you see that, for example, this village can be linked to this village by building a straight road, for example, that cut through this forest, right? And then can I do the same from this village to this big village by cutting another section of the forest and build another road? I can. But is that going to be good? You cut the forest twice in this case already, right? So why don't you do this? This village connected to this village via a road. Yeah, you have to cut the forest a bit. Then you just create a small road connecting these two villages, so that people here, if you want to go to this village, you go to this intermediate village first and then take the connecting road to this village. This way, you connect the three of them, and then you don't have to pay a lot to cut to build another road cutting through the forest again. Right. So that's an example of, and same thing here. So for example, this and this, there is a dense forest in between. So if you create a road that connects them directly, it's probably going to be costly. So why don't you connect this? Let me just write it down. Yeah, can you see the tree? Okay. Should I use another color? Yeah. Can you see now? Can you now see the tree? So having a tree, I'm sure that the graph is connected. Having a spanning tree, I'm sure that the graph is connected. It means that from every village, I can reach the other village via some roads. And then having minimum spanning tree will ensure me that this is the minimum way I need to fork out minimum amount of money to build this. Okay? That is minimum spanning tree. Okay? So some more definitions. So weighted graphs, where the graph have weights associated with edges. So previously we don't have it, now we have it. So it's just a function that maps a pair of vertices from vertex U to V if there is an edge, map it to a real number, so of a value. Then vertex V can be intersections, can be houses, something like that. Edges can be streets, roads, avenues, something like that. Most of them is undirected or two directional, and most of them will be weighted. The weight can be distance, can be time, can be tall or building cost for the previous slide, and so on. And we have a weight functions that maps edges to real numbers, and we have a notion of connected undirected graph. Means that the input is a connected graph in the first place. And spanning tree of a graph is a tree that spans all vertices in the graph, and that is the notion of weight of this spanning tree is the sum of this. A spanning tree has lots of edges, right? Some edges, right? The total cost of the weight of those edges will be the weight of the overall spanning tree. We denote it as W of ST. Minimum spanning tree of a connected undirected weighted graph G is the spanning tree of G with the minimum possible weight. This is the scientific notation of the problem. The idea is you are given a connected graph you want to form a spanning tree of this graph that has the minimum cost. So the informal standard MST problem is like this. You are given a connected, undirected, weighted graph. Connected, right? 0, 1, 2, 3, 4 can visit each other, connected. Weighted, because you have numbers associated to weight, to edges. The undirected, because 0, 1, 1, 2 doesn't matter. Your job is to select some edges of G so that the graph is still connected by the minimum spanning, minimum total weight. The edges that you select will form a spanning tree, and your output will be the minimum spanning tree of this graph. So without further ado, let's just look at one example. So this is the same graph. This is a spanning tree of this graph because 0 connected to 1, 2, 3, 4, and means that I have a tree that visits all vertices in this graph. So it's a spanning, it's a tree and a spanning tree. The total cost of this spanning tree will be 4 plus 4 plus 6 plus 6. Sum the red edges, the weight of the red edges, 20. This is not the minimum because I can have another spanning tree where I replace 0, 2 with 1, 2. This is another spanning tree. Why? Because it's a tree. It covers every vertices in the graph, and it has 4 plus 6 plus 6 plus 2, which is 18. The weight of this spanning tree is 18, and this is the minimum of all other possibilities. So 18 is the minimum MST cost, and this is one of the MST. Why I say this is one of the MST? Can you see that if I replace 0, 1 with 0, 2, I will get another MST that costs 18. So the MST is not unique, but the MST value, the weight of the MST is going to be unique. The minimum value is going to be unique, but the structure of the tree itself can be different. So, quick question. So, are the edges highlighted in red part of an MST of the original graph? True or false? Or what should we do if it's not true? No, we must replace 0, 3 with 2, 3. 0, 3 with 2, 3. Yep, right. That's the answer. That's the answer. The first one. Why? Because if we take out 0, 3 and replace it with 2, 3, I save minus 4. I save 4 more units, right? And I get a smaller weight, total weight, and I still get the spanning tree. If I replace 1, 2 with 0, 2, 1, 2 with 0, 2, I will actually increase the weight by plus 2. This bad. And then the first option, replacing 0, 3 with 2, 3, is the minimum possible. You can try any other possibilities. You cannot go better than it. So it's a minimum. So MST algorithm. MST is a well-known CS problem. It's so well known that in 1231 it becomes one of your example problems for greedy algorithms. And we are going to repeat that this semester for 2010. But to avoid too much repetitions, I will concentrate on the implementation side and application side of MST. So I will not go I will go faster in the next few slides because you have seen it before in 1231, regardless whether you still remember it or not now. Okay. Now, the algorithms are prims, or some people call Jarnik's prim algorithm. We are going to use priority queue to implement this. And then the second one is Kruskal. We are going to learn 2 more data structures. There are others. There are others that are too complicated for us to discuss in this course.
So we just concentrate on these two. So just a quick survey. Do you still remember this or not? You still remember prims or Kraskos? 29 of you says, I forgot. So only 2 says you have implemented them. Most of you haven't, right? By early October, by the time PS4 is due, I can confirm that you have done this. Regardless if you want or you don't want, you will have to implement this by PS4. Right? And for those who haven't took 1231, you have to catch up because I'm going to go fast in the next few slides. As fast as this. Okay. This is the pseudocode of frames. You read it yourself. I will show the animation. Okay. So this is how frames works. I will take a vertex. So what I'm going to say is the same as this slide. Same. I will take a certain starting vertex. Let's say vertex 0. For simplicity, let's say vertex 0. And I will enqueue all the neighbors, all the edges, outgoing edges of vertex 0. I will enqueue vertex 1, 0, 1, 0, 2, 0, 3, 0, 4. And I will order them based on edge weight. So I'm going to use product queue to help me do dynamic sorting. It's called dynamic sorting. So I have a pool of edges that I want to explore, and I keep adding new edges and on and on. I just want to concentrate who is the minimum. It's a kind of dynamic sorting. And then the other changes is when I store H01, I don't store vertex 0. I only store 1. And then the edge weight, 4 and then 1. When I store 02 with weight 4, I don't store 02, but I only store 42, the weight and the neighbor vertex number. When I do 03, I don't store 03 with weight 6, I just store 63. See that I don't store the starting vertex, I just store the weight of that edge and who is my neighbor. I store a pair of information. So can you verify that 41, 42, 63, 64 are the 4 edges outgoing from 0? Outgoing edges from 0, right? Okay. Now, among these 4 choices, I will greedy means you always pick the best at the moment. I will greedily select 41 because that's the frontmost item. 41 means H01, right? I will greedily connect them. I will connect 0 and 1 because this is the smallest H that I found so far. Okay. At the moment, see, I have a note. The sorted order of these 4 edges determine the final tree. It won't affect the minimum cost, but it will affect the look and feel of the spanning tree. Look at, if I swap 41 with 42, I will still get the sorted same final value at the end. But here, my sorting order is I first sort based on weight, and if it ties, based on increasing vertex number. So I will pick 01 at the moment. Now, can you see that I now have to enqueue 22, H12 with weight 2, but I only store 2, 2. And this dynamic sorting will place 2, 2 right in front of the other 3. Why the other 3? Because just now I take out 41, right? I take out 41, I left with 3. Then I insert 2, 2, and insertion of 2, 2 will place 2, 2 right in front of the priority queue. So I keep repeating the same process. I will take 2, 2, means that I will take this H12, and I will enqueue what? I will enqueue 2, 3. Why I don't enqueue 2, 0 again? Because 0 has been processed. 0 has been processed. So there is one more data structures. Every time a vertex has been visited, I will not touch, have been processed, I will not touch them again. So when I'm in vertex 2, I will not enqueue 2, 1 again because 1 is already there. I will not enqueue 2, 0 because 0 is already processed. So I will only enqueue 2, 3 with weight 8. Or in this case, I put 8, 3 because 8 is so large. 8, 3 will be at the back of the queue. Now I concentrate on who is at the front. 4, 2, right? But when I try to do 4, 2 means that this edge 2 is already done just now. So I ignore. The next best is 6, 3. I take them. 6, 3 means this edge. So I take it. And I connect 0 and 3. It is the current smallest. And now I have to look at 3. 3, 0 cannot because 0 is already done. 3, 2 cannot because 2 is already done. 3, 4 can with weight 9. So I'm going to enqueue 9, 4. Now who is the at front? 6, 4, right? So no violation, no violation. So I'll take 6, 4, and I'm left with 8, 3 and 9, 4. But then 8, 3 and 9, 4, all of 3 and 4 have been processed. So nothing will be done here, and the product is empty, and I should stop there. At the end, the MST that is formed is the minimum. That's how Prims works. So it uses product queue and a Boolean vertex, a Boolean array to flag whether a vertex has been processed or not processed. Okay. So you can take a look at this tool to help us understand again. Let's use a smaller. Okay, this is the same thing. Okay. If I run prims on vertex 0, I will consider the neighbors, pick the frontmost, take this, ignore that one, take this, ignore this, done. And I have this tree. And you can play around with this tool and draw your own graph and see what happens with prims. Alright, so to implement prims algorithm, you just need 2 data structures that you have seen before. You have seen priority queue. You can use Java priority queue. The enqueue pair of information. The first one is the edge weight, and then the second one is the neighbor number, the vertex number of the neighbor. And one simple 1D array to decide whether a vertex has been processed or not. So with this DSS, we can run prims in E log V. Why? By making sure vertex that has been processed will not be processed again, you will make sure that all edges will only be touched once. Look at this. At the beginning, 0 will process 0, 1, 0, 2, 0, 3, 0, 4. 4 of these edges will be processed in the first step. When I take this 0, 1, I'm going to add 1, 2. When I take 1, 2, see that I'm not going to process 2, 1 again because 1 has been flagged as true. I'm not going to process 0, 2 again because 0 has been flagged as true. I will only take care of 2, 3. 2, 3. Right? This one. This is a new additional edge. When I take out 3, I will not process 0, 3 anymore because 0 already flagged as true. I will not process 3, 2 anymore because 2 has been flagged as true. I will only take care of 3, 4. See that at the moment, all edges have only been touched once, So every edge will only be executed once. And what do we do for every edge? We insert and extract MAC from a heap, from a priority queue. This is log E. Because I have, at most I have E edges in my priority queue. I can do this in log E. But then E can be as big as phi squared. Right? So phi squared, you can drop the 2 down, so 2 log phi. You can cancel the 2, becomes log phi. Yeah. So I repeat again. Log E, this E can be replaced with phi squared. Phi squared, you can drop the 2 downwards because it's a power. Yeah, can go downwards. So 2 log phi. Then you can drop the 2. And it becomes log phi. And all this has been implemented in prims.demo.java. So can I show you that? Something like this. Okay. The code is just like this. The main part is here. This is the MST part. The rest is just a setup. You create a priority queue and a Boolean array, right? A Boolean array and priority queue, and then process for text 0. And while the priority queue is not empty, you process the rest, taking care of whether the neighbors have been processed or not processed. Something like that. Okay. So why this algorithm works? So if a greedy algorithm, it seems that we are not going to have a break. So why this algorithm works? Okay. Because it's a greedy algorithm, so it looks okay if we do it with one example like this, but will it be okay for all kind of graph? And for greedy algorithm, we will need a proof of correctness to verify that it will work for all cases. In 3230, you will see more of this. So what I'm going to do now is just to flash the two slides and go through quickly. You will see this again probably in 3230. So let's consider two trees, T and T accent, T and T star. Let T be the spanning tree generated by prim, and T star be the one that is known to have minimal cost. And you have two spanning trees. I say that in a graph, you can have many spanning trees. Let T be the one generated by prims, T star be the one that you know for sure has the minimal weight. If they are the same, prim is correct, right? If they are the same, prim is correct, definitely. If they are different, I can show you that whatever produced by prims can be transformed to T star with just minor tweaks. And that will say that anything that prims create will not be as worse, it will be equally good as what T star is. Something like that. So, I repeat, if T equals T star, we are done. Prim is correct. But if they are different, we'll do something. Okay, this is some notation. In the next few slides, next slide, I will have the pictorial representation of that. Okay. Let EK be the first edge chosen by prims at the kth iteration of prim algorithm that is not in T star. And let P be the... okay, let's just look at the graphs. Look at the picture. Okay. So the wording is in the previous two slides, and this is the visual explanations of what that wording means. Okay, suppose our prims algorithm reports T, and this is the one in red. This is T. I have 0, 1, 1, 2, 0, 3, 0, 4. This is T. And then suppose someone else say, no, that's wrong. The MST is T star. The MST is this. The MST is this. So at iteration 1, I have H01 that is chosen by prims that is not in the T star at the first iteration. Right? So I say E1 is 0, 1. Right? 0, 1. The path 0 to 1 exists. So 0 and 1 is the one that is reported by, is selected by prims, but not in the supposedly optimal MST T star. So how in the T star, how can I connect 0 and 1? Oh, I have to go to 2 and go to 1. That's the better way. So, say T star. So 0 to 1 in T star is the path taken by T star to connect 0 and 1. There is a difference, right? The difference is 0, 2. The difference is this edge. So if I substitute 0, 1 with 0, 2, I will get the same tree. I repeat again, I repeat this. Okay. Prims report a tree, T, and someone challenges you, this is not true, this is wrong, because the optimal MST must be T star. Then I can argue that there's a difference, right? You can see that there's a difference. The first time Prims spot the difference, say Prims takes 0, 1, whereas to connect 0 and 1 in T star, it detours 0, 2, and then 2, 1. It detours. There is a difference, right? And this difference is the H02. I can argue that if I replace 0, 1 with 0, 2, I will get T star. And doing so will not affect my the total cost, because 0, 1 and 0, 2 will be of the same weight. The difference between what Prims produce and what someone else says optimal at most will be the difference between ages with similar cost. Because ages with similar cost, you can take either one and get different MST, but of the same minimum cost. That's why Prims will always be correct. You will do something like this in a more rigorous manner in 3230 when you take it next year if you are a CS student. Next year or next semester. Okay. So we don't have this. It's 30 already. So I will continue with the other algorithm some of you may say, hey, can I just use Prims for everything? Because Prims can solve MST, right? So if you give me MST problem, why don't I just use Prims? This course, one of the syllabus that I am instructed to give is I have to teach you trade-off between various algorithms. So that's why for graph traversal, I don't stop at depth first or breadth first or either one. I give you two. And I tell you that one is better than the other in certain cases. Same thing with graph data structures. I don't give you a list for everything. Sometimes I say a matrix is better, sometimes list is better. So more options, more confusing for you. But it's for you to analyze the differences of these different ways and say which one is better given certain cases. So I'm going to make a little bit more complicated also for MSTs. I'm going to give you two options, two algorithms. And later for shorter span, I'm going to give you two algorithms also, Bellman-Ford and Dijkstra, and also breadth first, or three algorithms. So you have to analyze which one is better. Alright, so Crash-Curl, the pseudocode is like this, and how it works is explained visually like this. So this is the same picture, same original graph. I'm going to take out of many edges in this graph, I'm going to take the smallest, the one with the smallest edge weight. I have 4, 2, 4, 6, 8, 6, 9, right? The one with the smallest edge weight is 2, H1, 2. So I will just connect them, H1, 2. Then I will continue asking myself, at the moment, among those that I haven't selected yet, 4, 4, 6, 8, 6, 9, which is the smallest? 4, right? It can be either 0, 1 or 0, 2. In taking one of them, either one of them is fine. And it will generate different MST. Taking either one is fine. Let's say I take 0, 1. Now I need to ask myself again the same questions. Among those that I haven't selected, 4, 6, 8, 6, 9, which one is smallest? 4, 0, 2. But at this point, I cannot connect 0 and 2. Although it is the smallest, it has the next smallest edge weight. Because if I do that, I will form 0, 1, 2, 0, 1, 2 as a cycle of 0, 1, 2. I cannot have it. My tree cannot form a cycle. So I will ignore 0, 2. And among those that are still not selected, 6, 6, 8, 9, which is the next smallest? It can be 0, 3 or 0, 4, right? Suppose I take 0, 3. I will get this. Continue asking this until I can form a spanning tree. When I finish, this is the spanning tree. Continue. At the end, at this point, when I ask, can I connect 2 and 3? The answer is no, because if you connect 2 and 3, I will have a 0, 1, 2, 3 cycle, right? And then lastly, can I connect 3 and 4? No, because I'm going to have 0, 3, 4, and then I can have 0, 1, 2, 3, 4. No, I cannot connect 3 and 4. At the end, this is the spanning tree. This is the minimum spanning tree. So that's how Crash-Curl works. So you can take a look at the visualization again. So I have instructed Koji-chun to write two algorithms in the same page, so that when you draw a graph, you can run prims or classical and compare how the two behaves. I separate this into two files, you have to draw twice, but now you don't have to. On the same graph, if I run classicals, I will process the edges in sorted order based on increasing vertex width. 2, 4, 4, 6, 6, 8, 9, something like that. Every time I can connect the two, I connect. Every time I cannot connect them because of potential cycle, I will ignore. That's how classical works. So as simple as that. Right? So why this is work? Why doing so will produce an MST? Again, it's a greedy algorithm, and greedy algorithm always take the best, current best. It may or may not be the best in overall. So we will need a proof of correctness. So how? Okay, right. First, at every step of classicals, I will never have a non-tree. I will never have a non-tree. That's the first step. Why? Because classical algorithm has a special cycle check before ever adding a certain age into a current growing tree. So the edges taken will never form a cycle. So if we're going to form a cycle, I will ignore that edges. So at the end, I'm going to have a tree, right? After phi minus 1 edges taken, I'm going to have a spanning tree. So first step done. The way classical behaves because of the special cycle check. If adding E to T does not form a cycle, then there is this check, right? This if statement. Add E to T means that the T will never have a cycle. Never have a cycle. Okay. Now, second question that we have to ask: is this going to be minimum? Right? It's going to be minimum or not? So, the edges in the first place have been sorted from smallest weight to largest weight. So if the next unprocessed edge going to have a smallest edge weight and it has not be it's not going to give a cycle, then I can take it. If I replace it with another edge, so for example, now I am considering whether I have to take 0.3 or 0.4. If I take 0.3, I'm going to add plus 6 to my current cost. If I replace it with 0.4, I'm going to have the same plus 6, and it will not be worse than if I take 0.3. If I take others, like 8 or 9, it will be worse. So taking the edges in sorted order is a strategy that will never lose. It will always be as good as the optimal one. Right. So, and the pseudocode of classical is quite simple. First, you sort the edges by increasing weight. While there are still unprocessed edges, you take the one with the minimum cost, is the greedy part. If it doesn't form a cycle, you add that edge to the tree. At the end, tree is an MST. So to solve the edges, we will use a new data structure called edge list. I haven't teach you this, but it's just a simple graph data structure. And use any sorting algorithm that we have seen before. And finally, to test for cycles, we are going to use a data structure called union find. You will see this in week 7 during your labs demo. So edge list, what is this? Nothing more than just a list of edges. List of edges, yeah. And I will use integer triples to do this. I will store the weight in front, and then I'm going to store U and V next. So it's a triple information. I've introduced you with pairs. Now it's triples, three fields. So for unweighted graph, this can be stored as 0 or 1, or you can remove this part. But let's just have this field. The space complexity is clearly OE, because if you have E edges, you're going to have E rows. And why edge list is good for Kruskal? Because the very first step of Kruskal is sorting edges. Sorting edges not good with matrix, adjacent matrix, or edge list. But if you have a row of edges like this, it's not hard to sort based on the first field. It's not hard. You just need to have a comparator function inside your integer triple, right? Something like this. If the first element is not the same, you sort it based on the first value. If the first equal but the second one not equal, use the second field. Other than that, use the third field. By having this, then later on you can just use collection.sort. Collection.sort in Java. By having this comparator function, you will be able to sort these edges based on weight, because weight is your first field. If the weight is the same, like 4, 4 here, you sort based on the second field. If it's still same, 0, 0, you sort based on the third field, which is 1, 2. Then you break ties that way. Once you have this, you process the edges one by one. 2, 1, 2, 4, 0, 0, 4, 0, 2, and so on. Every time you encounter a cycle, prevent that. Every time you don't encounter a cycle, add it greedily. Yeah. Okay, this is the one that I mentioned just now. And for the second data structures, union find, you're going to use this. You're going to see this in lab demo on week 7. However, I have attached the file here in where is it? In the zip file. Yeah, you can see that this is the implementation of union find. Yeah. For now, let's assume that the cost for testing cycles using this data structure is negligible, it's constant. Therefore, this line is just O1 actually. Suppose this is negligible. It's very small, but can be considered as small enough to be treated as constant for our for medium-sized graph. For phi up to 1 million is just few steps only. So to sort the edges, we already need E log E. To test for cycles, we need some constant amount. In overall, it will be E log E plus E times small constant. Like you have to process all E edges in some amount of time. But the E log E will dominate. As E equals to phi square, you can again replace E with phi square, drop the 2 downwards, cancel the 2, you get the same complexity, E log phi. Okay. So Kruskal demo I've shown it that way. Quick fix. In the integer triple, where is it? Integer triple. The one that I uploaded don't have public, so you cannot compile. No, you have to make it public. This is just for displaying the content. Never mind. Right. So that's the discussion of minimum spanning tree. We will see this algorithm working in more details in tutorial sessions, in Lab 7, and your PS4. This is the first introduction of it. So see you on tutorial for if you are in my class, and or see you on Saturday for quiz 1. Okay, for those who want to do PS4 early, you are right by saying that you can use prims first. Because I haven't teach you union find, right? So you may be puzzled on how to use Kruskal. So you can start coding prims first for PS4. But by week 7, you will be able to know how to code using prims. Okay.
First question, where is the phase 1?
What time? It's 10 to 11:40.
11 in the morning.
10 a.m. to 11:40 in SR1, COM1 to SR1.
Okay.
method, 25 tests, 100,000. He runs in 8 seconds. So why don't you download this and test it for yourself? See that this forum is so active, so you miss a lot of information if you don't go here. There are a lot of test data already posted by your peers. Some of them I have verified, no, true, no different with mine. It means that his test is correct. If you can get the same answers with reasonable amount of time, mine is 10 seconds. It will good enough already. But if you got the correct answer but you didn't need to run in 10 minutes for example, then something is wrong. Go to discussion. PS4, PS3, what the other one?
Deadline is 24.
Where? In the CS?
Yes, yes. But the day is
Tuesday, 24 September.
Tuesday is 24th is a Monday.
Okay. So Tuesday, 25th. Tuesday, 25th. It's a typo. I will fix it. I will make it. I will announce it to the web. Did I put this correctly here? So this one also wrong. I will fix this Tuesday. Tuesday, 25th. So when are you leaving?
Friday.
What time of Friday?
Friday night.
And where are you going to come back? Sunday of the end of the festival. So you will be gone for 1 week. So where are you going? On 3 of you with Tom?
No, Tom will not be.
Only 2 of you.